In the previous chapter, we used the example of a ball falling down. This was pretty nice to show how we use simulink in principle. But to be honest, the example is not complex enough to be really interesting.
On the other hand, if I'm complicated, my wife doesn't find me interesting. But okay, let us add a spring to our ball and mount it to some fixing.
Okay.
The spring, right here I have a schematic. The spring is mounted in a way that at a position s equals to 0, it does not cause any force on the ball, the neutral position.
Yeah.
So for any s of the force caused by the spring, we can calculate the force as F spring equals to minus spring constant c times displacement s.
Okay.
So far, we only had a force acting on the ball solely caused by gravity g.
Yeah, okay.
And the equation was Fg equals to m times g. Now we've got a force caused by the superposition of the gravity force and the spring force.
Okay.
So our new equation now looks like F equals 2Fg plus Fs equals m times g minus c times s. We can enter this equation in our simulink model.
In the model, okay.
Let's switch to the model.
Yes.
Right here, this Fg will become the complete force, so let's remove this signal line for a moment. I make a little place by moving this to the right with the arrow key. And yes, now I need a sum block.
Yes.
The sum block is in the library common use blocks.
And somewhere down there.
Here it is.
Yes.
So right now, so one summand is the old gravity force, and the next summand we have to deal with very soon.
The force caused by the spring.
This will be our new complete force F.
Yeah.
And now I need the spring constant.
You just copy it using control copy and control V.
And this is not the orientation I would like, so under
in the context menu you've got the
flip
block.
This looks better. I need multiplication by minus c.
Okay, so you refer to the constant c and use it as minus c.
Minus c times s is the new force that I have to supply here.
To be added. And of course you have to add the constant c that we are referring to in the Model Explorer.
Yeah. Right now it would be 0.
Yes.
Or we would get an error message, I guess, if you would try it. So right here, Model Explorer, Model Workspace, add a new, and right here we take C.
And let's give it a value of, well, let's say 1.
Ah, you like the easy mental arithmetic.
Well, if you say your wife doesn't like you when you're complicated, let's do it the easy way.
My wife doesn't have anything to do with this. So, okay, we've got this model.
Okay. While the model is mathematically correct, the minus sign usually is not entered in the gain block representing the spring constant. The actual place experienced Simulink users are looking for the sign information is the sum block, as you see here.
Change it here.
Yeah, okay.
At the minus port.
Yeah. By double-clicking on the sum block, you see the representation of the signs in this block's input ports.
I just showed it again, yeah.
As you see, the two plus signs now represent two input ports whose values are added. By changing the sign of one input port in this representation, you can define that the value at one input port is subtracted from the other input port's value rather than being added to it. So removing the minus sign in the gain block describing the spring constant, and in parallel changing the sign of the respective input port of the sum block makes our model much easier to comprehend.
Yeah. And don't forget to really change the sign on the C again, because otherwise you have 2 times minus, which makes plus, and this is a completely different model.
Yeah. Good. Now it's a good time to run the model.
Okay, let's run this thing. So, oh, this looks strange. Whenever you have such straight lines in a simulation, of a continuous system, chances are very high that your fundamental simulation time is too big.
Yes, the fundamental simulation time at the moment, there's got a time step of 1 second. That's much too big, I think.
Too much. So let's decrease this. So we get
In
some
the model configuration parameters,
smoother curves.
let's decrease it to, say, 0.1 seconds.
And
Let's run it
rerun it.
again. Okay, let's
Auto-zoom.
auto-zoom.
So
Okay.
this looks very smooth, nice, but it's a little
it's
bit
not-
strange. Why should our displacement grow over time?
It's not as we expected.
So maybe
Maybe
It's
the,
smooth enough,
the
but
fundamental
still
time
not
step
right.
is still too big.
so.
Let's
Once
decrease it
again.
still by, let's 1 or 2 orders of magnitude.
So okay, let's add another one.
Okay, so it's now pretty small. Now it
I
should.
have a fast computer.
Yeah, now it should work pretty well. And still give it
So,
a correct
Right
auto
here we get the
scaling.
behavior we've been expecting.
Okay, that's the behavior we expect since there's no damping, so the amplitude just remains the same.
By the way, for those interested in solver methods, if I change here to the Rummikutta, I could have a much bigger simulation step.
Okay,
And it
0.1,
will
that's
still
really
work.
big. So it's a more sophisticated solver who can work with bigger time steps.
But we only explained the Euler, so we
So
stay with Euler.
Let's go back to the Euler, yeah.
You know how
Yeah.
many zeros we had?
I think we're 3.
Yes.
You've got
I
the
just
decimal
pulled it up.
point, yeah. And go back to the Euler before, stop, go back to the Euler,
Yeah.
please. So
You see?
that's as we did it.
Just to check that everything's okay again. Right
And
here
it works
is
nice.
Wonderful.
Okay, great.